Welcome back. In the last class, I introduced to you about interaction parameters of NMR, both external and internal. In the internal interactions that are present within the molecule, I told you about chemical shifts, scalar coupling, dipolar coupling, and for spin-off nuclei, spin greater than half nuclei, the quadrupolar couplings. All those things we discussed. And I was telling you more about chemical shifts, why it comes and everything. We'll start discussing more about chemical shift from today. First of all, chemical shift, how does it arise? The nucleus of an atom is surrounded by the electron clouds. Please remember that. The nucleus of an atom is surrounded by electron clouds. It is not a bare nucleus. So what is going to happen is there are two interesting phenomena takes place simultaneously. When you put the molecule of your interest in the external magnetic field, there is a very big magnetic field. The external field induces currents in the electron clouds of the molecule. It induces current. See, electrons start flowing like this. It induces currents in the electron clouds. Subsequently, what happened? The circulating molecular current in turn generates the magnetic field. There are two things are happening. Please remember. The electrons start, external field start inducing the currents in the electron clouds of the molecule. And this circulating current in turn generates magnetic field. So that means in addition to the external magnetic field, there is some other field which is produced within the molecule. Now what happens to this field? Does it add to the external field or subtract to the external field? Because of this, the nucleus which is at the center, what is the field it is going to see? It is going to see B naught alone, or B naught plus the field generated by this, or B naught minus the field generated by these electrons. That we'll have to understand. So the nucleus sees external field plus the field induced because of the electrons. These are the two important things. Please remember. Okay. So now electron shielding around the nucleus is like this. Look at a bare nucleus. Assume there is no electron at all, a bare nucleus. It feels the full effect of the external magnetic field. The external magnetic field B naught is here. It sees the full effect of it. There is no other thing which is coming into the picture in between nucleus and the magnetic field. Now consider there are certain electron density, let us say, surrounding this nucleus. There are electrons moving around the nucleus. This electron density partially shielding this nucleus. So in addition to B naught, it also sees some local field. The nuclear spins see this local field in addition to external B naught field. Okay, it sees the local field, and this induced field is generated by these electrons. Are always the induced fields opposes the magnetic field, that is main magnetic field B naught. Please understand the point. Bare nucleus sees the complete effect of the external magnetic field. If you have electrons moving around this nucleus, the surrounding this shields the nucleus, and the nuclear spins also sees the local field. This local field is coming because of the electron which induces this field, which is called a small field induced field Bi. It opposes the main magnetic field B naught. So what is going to happen? Since this main magnetic field is opposing that, the electrons are said to shield the protons, or electrons are said to shield the nucleus. Okay, it is shielding, a sort of a shield, so the nucleus cannot directly see this one. Something is coming in between it, something is shielding. So the electrons shield the nucleus, so the nuclear spins do not see the external field fully. It also sees the local field produced because of the electrons. So, and this local field, as I said, it opposes the main magnetic field. We can say the local strength of the local field is B naught minus induced field. Okay. The induced field generated by the electrons opposes the main magnetic field, I said, and that's the reason why we say electrons shield the proton. And the local field is reduced by a small amount. What is that small amount? The field seen by the nucleus is reduced by a small value, that is B naught into 1 minus sigma I. That is an equation. Okay, the local field you can calculate, which is B naught into 1 minus sigma I. And sigma depends upon the type of nucleus. It is different for different nuclei depending upon the charge density surrounding the nucleus. Please remember, sigma is not same. In the example of the molecule you took, the sigma will be different for CH group, different for NH2 group, and different for CH3 groups. That as a consequence, the local fields for different groups are different. Though you have one molecule, you have different functional groups. As a consequence, each functional group has a separate local field. That is because they have a different sigma values. Remember this point. So the effective magnetic field, if you express like this is called a screening factor, also called a shielding factor, which is directly proportional to the electron density surrounding it. So higher the charge density, higher the gamma, higher the sigma. Remember this, the shielding factor is larger and larger because it is proportional to the electron density surrounding it. If there is more and more electronegative nucleus, more electrons are there, more charge density at the site of the nucleus, this is larger and larger. What is the value of the sigma? Typically, it is of the order of 10 to the power of minus 5 for protons and around 10 to the power of minus 3 or less for other nuclei. Okay, so value for gamma, value of sigma for protons is 10 to the power of minus 5. The proton sigma is always positive. Okay, it is positive. There is a way you can calculate sigma, everything. Let us not, there is a huge discussion we can do, lot of discussion can be done on chemical shifts, how to calculate sigma. We go more and more deeper into the theory. Let us not bother about it for our course, just for understanding. Please remember, for protons the screening constant or the shielding factor is always positive, and the semi-empirical value is 26.6 into 10 to the power of minus 6. This is the semi-empirical value. I'm just quoting without going into the details of how we calculate this thing. Okay. Now, to determine the shielding constant, we also use a formula. You may ask me a question, how did I get this 26? I said I don't want to go into the theory. I simply give you the one formula. This is called Lamb's formula. Okay, the formula given by Lamb. This is Lamb's formula. This gives shielding constant for an isolated proton which is perfectly spherical. Take a hydrogen nucleus, proton. I showed you in the first example, a bare nucleus, no electrons at all. An isolated proton is always perfectly spherical. Okay, this shielding constant. For other molecules also, in principle, you can use the same formula to generate this. But you must know a factor called rho of R. That is an important factor in this formula. It is not easy to know this for all the nuclei, if other than protons. But qualitatively, we know these values. As we go ahead, I tell you, it depends upon several factors called diamagnetic contribution coming because of s electrons, paramagnetic contributions coming because of p orbites, p electrons, etc. So we can, and also it depends upon the neighboring functional groups attached to the proton of our interest. So various factors add to this. So sigma can be calculated accordingly, but this is a general formula. You remember, if you want to know how screening constants are determined, what is the shielding constant, there is a general formula called Lamb's formula which is utilized. Okay. Now let us look at the electron density, how it affects the different nucleus, how different nucleus see the different charges surrounding it based on the functional groups. As I said, where nucleus in the absence of electron, it is perfectly spherical, uniform charge distribution surrounding it. Okay, charge distribution is perfectly spherical and uniform, no problem at all. Look at this one. I have taken a nucleus. If you can carefully see, there is a gray color circle here, which is depicting the charge distribution. This is also spherical. You understand? I'm taking the example of the nucleus, where the charge distribution of electronic surrounding it is also spherical. Spherical cloud of electrons. There also you will see it is uniform. No problems at all. But in the molecule, you don't have proton alone, single proton, or you don't have a bare nucleus alone. You always have molecules where different atoms are bonded. We have a bond. There are different functional groups attached to it. It is not just one bond. There may be several bonds, several groups may be attached. As a consequence, in such groups, the charge density is not always spherical. Now, look at this CH bond. The charge distribution in this case is spherical, but you see here the gray colored drawing what you are seeing is elliptical in shape, because the charge of this charge density at the site of carbon, at the site of nucleus, you have to see the total charge distribution. If you see at the site of this entire CH bond, it looks like an ellipsoid, elliptical shape. It is there. It is symmetric ellipsoid. Okay, that is one thing. Whereas, now come back to this one. OH. Oxygen is attached to hydrogen. Now, oxygen is more electronegative. You all know that. Oxygen is an electronegative atom. And because of this, the charge density, charge distribution is not symmetric like spherical circle, or not as a symmetric ellipse. It has a different shape. The more charge density is at the site of the oxygen, which is electronegative, and it is less here, the oxygen pulls the electron of the hydrogen towards it. The charge density is not like this, it has a different shape. Okay, we'll go one more step further. For the OH, we'll add another bond, O double bond C, join this with OH. It's some hypothetical molecule. Don't worry whether it is practically feasible molecule or not. Let us look at this type of bond. The charge density, OH we knew. Now this O and carbon is different compared to proton. And you see the charge density, if you look at it, here electron, this oxygen with us more charge for this proton, it is more electronegative, and compared to this carbon. Okay, this carbon also has depleted charge here at the site of this carbon nucleus. So like this, different functional groups, if you study at the site of a particular nucleus of your interest, you see the arrows which depicts here, the charge densities will be different. More the electronegative atom attached to it, more electrons are depleted here at the site of the hydrogen. It withdraws the electrons from it. It's the electron withdrawing group here. Okay. So of course you can also have an electron donating group. Then it will have more charges at the site instead of depleting. So like this. Now all this what I'm trying to say is these electrons will induce a field. Okay. Now the question is, because of the different charge distribution, how much is the induced field? Remember the induced field, the B local we found out. Because of the induced field, the B local is different. It electrons induces the field, and the nuclear space is the B local field. What is the induced field strength? We have a external magnetic field I told you whose strength is of the order of several Tesla. Whereas, what is the amount of the field produced, induced field here? Let us calculate. We can even calculate. Let us say I have a 400 megahertz spectrometer, which correspond to magnetic field of 9.3949 Tesla. I have taken up to fourth decimal place. Let us keep it only this much accuracy. Understand? For 400 megahertz spectrometer, the field is 9.394 Tesla. You know 1 Tesla is 10 to the power of 4 Gauss. When expressed in Gauss, it is 93949, 93,949 Gauss. But you can calculate the field induced. You know how much is the field induced? It is 0.00005 zeros after decimal, 93949 Gauss. Very small, negligibly small. The total magnetic field experienced by the nuclei is now 93,439.000093949 Gauss. My God, such a small field. But then what is going to happen? Your resonating frequency is not just 400 megahertz. 400 megahertz was for this field. Small field induced by the surrounding electron adds to this main field. Of course, as I said, in induced field opposes. I will tell you more about it. I am taking the example here, just for addition of this value, just for the calculation purpose. The resonating frequency is now just not 400 megahertz. It is 400 megahertz plus 400 hertz. You see, this you can calculate. For this magnetic field, what is the resonating frequency? You can calculate it is 400 hertz. For this magnetic field, it is 400 megahertz. For the total magnetic field of 93439 plus, sorry, plus this value, totally this value 9349.50, 93439 Gauss. The resonating frequency is not 400 megahertz but 400 megahertz plus 400 hertz. You understand? So resonating frequency of protons, instead of exactly at 400, is now shifted by 400 hertz. You understand? To the electronic charge distribution, it is shifted by 400 hertz. I said here plus 400, even though it induced field opposes. You take minus 400, doesn't matter. Again, it is shifted by 400 in the opposite direction, doesn't matter. That's why I did not bother about this sign, whether addition or subtraction in the previous slide. The resonating frequency consequence is that the resonating frequency of the protons is shielded and I'm sorry, shifted by 400 hertz. Okay, and because it is shifted due to the chemical environment of this nucleus, it is called chemical shift. Please remember, the resonating frequency of the protons is shifted by 400 hertz in our calculation because of the electronic charge distribution due to the chemical environment of this nucleus. It is called chemical shift. The chemical environment shifted this peak. Now, what happened to the different functional groups in a molecule? There are varieties of functional groups. How do they shift? Consider now the example of a molecule like this. In the very first example, very first slide I showed you in chemical shift, this one has 3 different functional groups. But when I went into my equation, I showed it all gives rise to single peak. But now what is happening is the shieldings are different. Electronic environment at the site of Ca3 is different. At the site of NH2 is different. At the site of CH is different. I have written the shielding electronic cloud has a bigger umbrella here. It's much more shielded because of 3 protons than NH2, which is 2 protons, of course, with the nitrogen, and CH proton has a smaller shielding. The umbrella size here tells you the extent of shielding. Larger the umbrella, larger the shielding. Okay, so now what it means is the field seen by these 3 different types of protons are not same. It's not just only B naught. It is in addition to B naught plus induced field. You can understand the point. In the previous slide, I did not bring in the internal interactions. I said all were same. That's why I said it will give a single line based on this equation. But now we have understood the internal interactions. As a consequence of different charge distributions, these frequencies are not same. And I can tell you the resonating frequency for CH3 is less than CH and is less than NH2. That means the fields seen by these different functional groups are B naught plus induced fields which are different. As a consequence, you don't get single peak now for this molecule. You get three different peaks. One peak for CH3, one peak for NH2, and one peak for CH. And remember, I have written something different here. They are coming at different places because they experience different magnetic field that are called as chemical shifts. And in addition to coming at different resonating frequencies, I have written different intensity for these peaks. You will understand that later when you go ahead. Okay, that also you should remember that this corresponds to this intensity of the peak also tells me the number of protons present. This is for 3 times intensity for this. It should have been CH and this should have been NH2 because this is 2H 2 times intensity. I have made a mistake. Don't worry. This should be CH2. This is NH. This is CH. This is NH2 and this is CH3 in my drawing. Or I can, if it comes downfield, I have to make this as double the intensity. It doesn't matter. And this is how the spectrum looks. So what you are understanding? Nuclear spins do not get involved in the chemical reaction. We all know when you are doing chemical reaction, we always talk about electrons, how the electron is moving, how the reaction is taking place. Nevertheless, nuclear spins gives information about the chemistry of the molecule. That's what we understood in the previous slide, because the charge densities are different and we get different peaks. So you can understand more about the chemistry of the molecule by seeing the NMR spectrum, which is due to nuclear spin. Although nuclear spins do not get involved in the chemical reactions. So this is an important point which I wanted to tell you. Next, another thing, information I want to tell you, all the measurable NMR parameters from the spectrum are anisotropic. I told you this, I discussed last time also about when I introduced chemical shift, dipolar coupling and J coupling. Every parameter is anisotropic, orientation dependent. And I said some of these things motionally get averaged out, some are not. But these are the 4 important parameters which we get. And these parameters, when different measured in different directions, have different values. So now the charge density distribution at the set of the nucleus is not always spherical and can be seen as a ellipsoid. Okay, so that's why the value depends upon the direction of orientation of the long arcs of this ellipsoid. In the case of isotropic motion, isotropic solution, there is a motional averaging. As I said, these two things get completely averaged out. So what does it mean? The rapid isotropic motion in solution averages out all this orientational dependence. The measured chemical shift value in the solution state is the isotropic average. You get only single value. You don't get chemical shift. What you want, in principle, you would have got different values when you measure in different directions. If maintain the anisotropy, but in the solution stable, anisotropy is averaged out. So the chemical shift what we measure is the isotropic average. Okay. What happens if there is no isotropic average and it is only partial average, not complete removal? In which case, all these anisotropic parameters gets into the spectrum. Please remember, only when in a solution when the perfect motional averaging, totally all these anisotropic parameters will go to 0. That is the isotropic spectrum. If it is not averaged completely, there is a partial averaging. It's possible, There are some anisotropic media, I said in one of the classes like liquid crystal. These anisotropic parameters will get reflected in the spectrum and causes severe line broadening. Okay, so now we will understand how different electron densities affect chemical shifts. Consider a methane group. We have only single proton. The charge distribution is corresponding to only one proton. Okay. Now, effective field seen by the nucleus is more than the static field. B effect is more than B naught. I understand. Now, go to methyl group. There are three protons. The charge density is different from CH proton. It is due to three protons now. The effective field seen by the nucleus is more than that of the B naught here also. Remember, the effective field seen by this nucleus is different from B naught. Effective field seen by this nucleus is also different from B naught. Then what is the difference between these two? The difference is B effective of methyl is more than B effective of methane because this has more charge density distribution. So methyl protons, I would say, are more shielded. The shielding, because is much more here, methyl nucleus has three surrounding electrons. If it has to see the main magnetic field, it has to cross this barrier. You remember? So it is more shielded than CH. What does it mean? The effective field seen by methyl protons are more than that protons. Essentially, it means CH3 protons resonates at a high field because the field is more. Field seen is much more. So it resonates at a high field than CH proton. You understand? Based on the charge density distribution, you can even say which proton has higher resonating frequency and which proton has a lower resonating frequency. In this simple example, we knew methyl protons has more shielded than CH protons. As a consequence, effective field seen by these methyl protons are more than that of the methane proton. So CH3 protons resonate at higher field than CH proton. Get the point? So today I'm going to stop here and I have given you the brief idea about the reasons for seeing the chemical shift, the conceptual understanding of why chemical shift arises. It is because the motion of electrons, and I said the field induces the motion. The motion of the induce the motion on the electronic clouds, and which in turn generates the magnetic field, which as opposes the main magnetic field. I said, and then we saw varieties of charge distributions for different functional groups, and how different charge density distribution causes the effective field seen by different nuclei. And we took the example of the CH3 and CH protons, and we said CH3 protons are more shielded than CH protons. As a consequence, we said CH3 protons resonates at higher field than CH proton. So we'll stop here. In the next class, we'll talk more about chemical shifts and their interpretation and everything.